is x equals L, and this entire width of our box is equal to L. So we basically want to focus on the point 0.25 L and 0.75 L, and we want to find the probability of finding our electron within this region. Now, what exactly is the meaning behind this curve? So this curve, which basically is the probability distribution of the electron in the ground state n equals 1, represents the probability of finding our electron. So if we basically take the lower boundary to be this quantity and the upper boundary to be this quantity, and we integrate, that will give us the area as shown in the following shaded region, and this would represent the probability of finding the electron between these two positions. So we basically want to integrate this function with respect to x, beginning at this position and ending at this position. So the shaded area is equal to the integral of the lower boundary to the upper boundary of our function, the square of absolute value of psi with respect to dx. So because psi is equal to this quantity, we replace psi with this, and we square it to get the following result. So now we follow the same exact steps that we took in the previous lecture. So we basically want to replace x with theta. So we set theta equal to n pi divided by L multiplied by x. And now we integrate both the left and the right side. Or we take a derivative of the left side as well as the right side. So derivative of the left side is d theta. Derivative of the right side is n multiplied by pi divided by L dx. So now we take this and solve for dx. And we see that dx is equal to L divided by n pi multiplied by d theta. So the entire point of this step was basically to find what our theta is in terms of x, and then rearrange and solve for x in terms of theta as well as dx in terms of theta. So we see that the shaded area is equal to, so a squared is a constant, we can bring that outside of our integral. So a squared multiplied by the integral. So the lower boundary becomes 0.25 pi, and the upper boundary becomes 0.75 pi. Now this becomes sine of our theta squared. So we replace this inner portion with theta, and we replace dx with this quantity. So L divided by n pi multiplied by d theta. So this is a constant, we can bring it outside of our integral, and we get the following result. So next we apply a trig function. So we know that sine of theta squared is equal to 1/2 of 1 minus cosine of 2 theta. So we take this sine 2 theta, and we replace it with 1 minus cosine theta, and we take the 1/2, and we bring it outside of the integral because it's a constant. So now we get this result. The next step is to actually integrate. So this becomes theta, and this becomes sine 2 theta divided by 2 as shown in the following region, and we basically evaluate the integral from the lower boundary to the upper boundary. Now, if we actually evaluate the integral, we get the following result. And if we calculate this, we get 2.571. Now notice A, the amplitude is equal to the square root of 2 divided by L. So we replace A squared with 2 divided by L. So notice the L's appear on top and bottom, and so do the 2. We can cross out our L's and cross out the 2's, and we simply have 1 divided by pi multiplied by 2.571, and that gives us about 0.82, or equivalently 82%. So that basically means the probability or percentage of finding our electron between these 2 points along the bottom portion of the rigid box is given by 82%. In this lecture, we're going to analyze and interpret the results we obtained from our discussion of a particle moving in a rigid box, also known as an infinite potential well. So let's suppose, once again, we have a free particle with mass m that is moving inside the following rigid box. So we have the right and left wall of the box, and the particle is moving only along the bottom of that box. So this is the x-axis, and this is the y-axis, where the y-axis represents the potential energy of that free particle, and the x-axis represents the position of that particle along the bottom portion of our box. Now, the left corner of the box is given by x equals 0, and the right corner of the box is given by x equals L. So the width of the box is given by the distance L, and the particle moves between the 2 corners of the box, and at any given point between these 2 corners of the box, the potential energy of that particle is given by 0. Now, previously we saw that the wave function psi of x, that represents our motion and behavior of that particle with potential energy of 0, is given by this equation. So psi of x is equal to the square root of 2 divided by L multiplied by sine of pi multiplied by n divided by L times x. So this is once again the wave function that describes the motion of this particle. This describes the wave that is produced by our free particle. Now, what exactly is our meaning of n? So n represents the quantum number of our particle. It's a positive value. It could be 1, 2, 3, 4, and so on. Now, L represents the width of our box. It's the distance between our 2 corners. X represents the position of our particle between these 2 points. And finally, the square root of 2 divided by L represents the altitude of our wave produced by this particle. Now, recall that if we take the square of the absolute value of the wave function, if we take the square of the absolute value of this entire right side, that will give us the probability density, the probability distribution of our particle as it moves between these 2 positions. So let's suppose our quantum number n is equal to 1. Let's graph the probability density versus the position of our particle as it moves within the following box. So we get the following diagram. So once again, the y-axis is the square of the absolute value of our wave function. It's the square of the absolute value of this quantity, and the x-axis represents the position of our particle between our 2 corners of our box, where this is x equals 0, and this point is x equals L. So we get the following distribution. So what exactly is the meaning of this distribution? So notice that in this particular point along our distribution, this represents the highest point of our probability density. So that means at any given moment in time, the particle is most likely to be found at this position along our x-axis, directly at the center. Now, if we continue that with n equals 2 and n equals 3, we get 2 humps, and then we get get 3 humps. So for this particular case, at any given moment of time, our particle is most likely found at this position, and is not likely to be found at the center as in this case. Now, if we continue with n equals 3, we get the following diagram. So basically, these 3 graphs represent the probability density of our particle as it moves along the rigid box, where the y-axis gives the value of the square of the absolute value of this function. Now, from these graphs, we see that the particle is more likely to be found in one place than in another. Specifically for this case, in quantum mechanics, we see that the particle for quantum number n equals 1 is more likely to be found at the center, at the middle of that one-dimensional rigid box, than at the corners. So at the corners, there is a 0% probability, of finding our particle, but at the center, that is where our particle is most likely to be found. Now, let's consider one type of application of this in the real world. Let's consider an electron moving back and forth along a flat, thin piece of metal. So we have our very flat piece of metal, and the electron is moving back and forth, as in the case of the one-dimensional rigid box. So based on the argument above, the electron will most likely be found at the center of our metal at any given moment in time. So that's what we can interpret from all this information. Now, let's move on to the amplitude. So earlier we said the amplitude is equal to the square of 2 divided by L, and this basically tells us the height of our wave that is produced by this particle. And if we square that value, if we take the square of the absolute value, that gives us basically the height of our amplitude. So it gives us the height of our probability density value. So the amplitude from this equation tells us that it only depends on the width of that box, and that is given by L. So as you decrease the width of the box, you increase the amplitude of that wave. So if L decreases, if the box gets smaller along the x-axis, then the amplitude of the wave produced, this quantity will increase. And because this increases, the square of our absolute value of our wave function will also increase. And so that will increase the probability of finding our electron or our particle at the center of our box for the case of n equals 1. So once again, for the case of n equals 1, let's suppose the y-axis is the square of the absolute value of our wave function psi, and the x-axis is our position along the x-axis, which is given by our distance L. So for this particular box, with a width of L, we have the following hill produced, but for this case, where we increase our distance to 2L, we see that because the amplitude decreases, that will decrease the wave function and will decrease the square of the absolute value of that wave function. So our hill will basically decrease, and we see that now there is a smaller probability of finding our electron, our particle, at the center than in this particular case. So that is the relationship between the amplitude, with L, as well as the probability. And finally, let's move on to analyzing the energy. So in the previous lecture, we saw that E is equal to m squared multiplied by h squared divided by 8 times m times L squared, where L once again is the width, m represents our mass, and h represents Planck's constant, and n represents the quantum number of our particle. Now notice, for any particular box that has a fixed L value, this quantity will be a constant. So h squared divided by 8 times m times L squared is a constant as long as our L, the width of the box, is a fixed value. And we see that the energy of the particle for any given quantum number only depends on the quantum number itself as long as our L is fixed. So that basically means if we plot the following diagram where our y-axis is the energy and the x-axis is our position, so our width of the box is a fixed value and it's given by L, then if we increase our n value, we see that the energy will jump from this quantity to this quantity, then to this quantity when we increase from n equals 1 to n equals 2 to n equals 3. So this is basically in accordance with the quantum theory of energy. That is, we see that energy is quantized. It exists in discrete units. For example, the energy cannot be found anywhere between these red lines. The energy of our particle for n equals 1 lies along this axis, for n equals 2 it lies along this axis, and for n equals 3 it lies along this axis. So each red line represents the energy associated with each quantum number, and we see for any given fixed L, this equation becomes as follows. So En is equal to m squared multiplied by E1, where E1 is simply the quantity of energy of our particle in the rigid box when our quantum number is equal to 1. So if we take the energy value of this and multiply by n squared, that will give us the energy of our particle for some other n quantum number. In our discussion of particles inside rigid boxes, also known as infinite potential wells, we said that the wave function that represents our particle inside the rigid box is given by this equation. So the wave function is equal to the constant A multiplied by sine of n pi divided by L multiplied by x, where x is the position of the particle along the bottom portion of the box along the x-axis, and is the quantum number, pi is a constant, and L is our width of that rigid box. Now A, as we said, is a constant, and we saw in a previous lecture that A is equal to the square root of 2 divided by L, where L is the width of our box. Now we also said that constant A represents the amplitude of the wave produced by our particle. The question is, where exactly does this equation come from? So in this lecture, we're going to derive this equation using a concept known as normalization. So recall that for any wave function in quantum mechanics to actually be physically meaningful and measurable, we have to normalize that wave function. So in this lecture, we're going to use the concept of normalization to find what the equation for A is. And that's exactly why another name for A is known as the normalization constant. So let's begin with step 1. So recall that by definition, what it needs for a wave function to be normalized is it has to satisfy this equation. So this is the integral from negative to positive infinity of the square of the absolute value of the wave function with respect to dx is equal to 1. So for our wave function to be normalized, this has to be true. The left side has to equal to 1. Now, let's actually take the right side of this equation and replace psi with the right side. So we get this, which is equal to, so our A is a constant, we can bring that outside of our integral, and we get a squared of the integral from negative infinity to positive infinity of psi of npx divided by L squared of dx, and this is equal to 1 by our process of normalization. Now, notice, we can replace the negative infinity with 0 and the positive infinity with L. And that's because if we have a rigid box with a width of 0 to L, if the width is given by L, then the particle will only be found within this region. It will not go above L, and it will not go below 0. So we can replace our negative infinity with 0, and we can replace our positive infinity with simply L. And this is still equal to 1 by the process of normalization. So to actually solve this integral, we basically have to replace our x with the angle theta. So let's set our angle theta, which is the inside of this quantity, equal to n pi divided by L multiplied by x. So this basically becomes theta. Now what exactly is dx? So let's take the derivative of these two sides. So we take the left derivative with respect to theta and the right derivative with respect to x. So we get d theta is equal to n pi divided by L multiplied by dx. So we want to solve for this dx. So we rearrange and solve for dx, and dx is equal to L divided by n pi multiplied by d theta. So dx is replaced by this, as shown in the following step, and the inside of the sine squared is replaced with simply theta. Now notice, the lower bound stays at 0, and the upper bound is now n multiplied by pi. Now n multiplied by pi comes from the fact that the sine of n multiplied by pi, where n is a positive integer, is always equal to 1. That basically means our particle cannot go above L and cannot go below 0. Now, let's actually bring the constants that appear on this side of the integral outside the integral. So we have a squared multiplied by L divided by n multiplied by pi, and we multiply that by the integral from 0 to n pi of sine 2 theta d theta, and this is once again equal to 1. Now, once again, A is our constant that we're looking for, known as the normalization constant. L is the width of our rigid box. It's a fixed value, and it's also a fixed value. It's the quantum number, and pi is simply our constant. Now, to actually solve this, we're going to apply a trig function. So recall that sine theta squared is equal to 1/2 of 1 minus cosine 2 theta. So we basically take this sine 2 theta and replace it with this quantity as shown in the following step. So next, we actually integrate, and we see that a squared L divided by 2 and pi, where this 2 comes from this value, is equal to theta minus sine of 2 theta divided by 2, because the integral of cosine is simply sine. So we evaluate the integral from 0 to pi n, and we set that equal to 0. So if we evaluate this integral, this inside simply becomes n multiplied by pi. So a squared multiplied by L divided by 2 and pi multiplied by n pi is equal to 0. Now these two quantities will cancel, and if we solve for a, we see that the amplitude of the wave, also known as the normalization constant, is equal to the square root of 2 divided by L, which is exactly this equation that we mentioned previously. So once again, this a represents the amplitude of our wave function, of the wave produced by the particle inside our infinite potential well, also known as the rigid box. And because we use normalization to find what the equation for a is, this a is also known as the normalization constant of the particle inside our rigid box. In this example, we're going to apply the concept of a particle in a rigid box to a molecule moving in some region of space. So suppose a water molecule is confined to a one-dimensional region of width given by 1 millimeter. So if we treat the water molecule as a particle inside a rigid box, in part A, we want to find the energy of the molecule when it is in the ground state, and in part B, using the principle of equal partition of energy, we want to determine the quantum number of the water molecule at a temperature of 310 Kelvin. So let's begin with part A. So because we're basically treating our water molecule as if it was moving within a rigid box that has a width of 1 millimeter, we can apply the following equation that gives us the energy of our particle, of our water molecule, for some particular quantum number n, for some mass m, and for some width given by L, where h is Planck's constant. Now, because it tells us that the water molecule is in fact in the ground state, that means the quantum number n of our water molecule is equal to 1. Now, to find the mass of the water molecule, we basically take the mass of our water in grams per mole, and we divide that by Avogadro's number, and then we take that and multiply that by 1 kilogram in 1,000 grams. So the grams will cancel, the moles will cancel, and we're left with about 2.99 times 10 to negative 26 kilograms. So this is the mass of a single water molecule in kilograms. So now we are ready to apply this equation. The energy of our water molecule in the ground state is equal to the square of Planck's constant divided by 8 multiplied by the mass of the water molecule in kilograms multiplied by the square of the width of our rigid box, the region along which our water molecule is moving on. So we divide and we get about 1.84 times 10 to negative 36 joules of energy, which is equivalent to about 1.15 times 10 to negative 15 electron volts. So this is basically the lowest amount of energy that is found in our water molecule when it's moving within this confined region of space. So next we move on to part B. So now we want to apply the principle of equal partition of energy to determine the quantum number of the water molecule at a temperature of 310 Kelvin. So basically, according to the principle of equal partition of energy, the average thermal energy of a single molecule is given by this equation. So K multiplied by T divided by 2, where K is the Boltzmann constant and T is the temperature given in kelvins. So the Boltzmann constant is given by 1.38 times 10 to the negative 23 meters squared multiplied by kilograms divided by second squared multiplied by kelvins. And we multiply that constant by the temperature given in Kelvin. So 310 kelvins, and we divide that by a factor of 2, and we get about 2.139 times 10 to negative 21 joules. So now we know the energy that our water molecule has at a temperature of 310 kelvins. So now we apply this equation to basically determine what our quantum number is. So the energy of our water molecule at some fixed width given by this quantity is equal to m squared multiplied by the energy of that same water molecule at a quantum number of n equals 1. So we found what E1 is in part A, and we know what En is. That's given by this value. So now we solve for n, the quantum number, and we see that n is equal to the square root of En divided by E1. So En is equal to this quantity, and E1 is equal to this value. So we divide, take the square root, and we get a quantum number of about 3.41 times 10 to the 7. So this is the quantum number of our water molecule that has an energy given by this quantity, where the lowest possible energy of that particle at a quantum number of n equals 1 is given by this quantity. So we see that the concept of the particle in a rigid box can be very useful in making calculations on the subatomic and atomic levels. In the previous several lectures, we discussed a particle moving inside a rigid box. So basically, a particle inside a rigid box, also known as an infinite potential well, is confined to that box. It cannot move outside our rigid box. Now let's discuss a slightly different case. Now let's examine the motion of a particle inside a one-dimensional box that is not rigid. That is, the particle is allowed to move outside that box, and the potential energy of the particle outside the box is given by a finite quantity. So, to see exactly what we mean, let's look at the following diagram. So basically, we have the y-axis, which gives us our potential energy u of our particle, and the x-axis represents the position of our particle along the one-dimensional axis. So basically, the left wall of the box lies along our y-axis, and the position of the left wall is given by x equals 0, while the position of the right wall is given by x equals L. So let's basically divide our regions into 3 different regions. So region 1 is given by the following section. So basically, if the particle is found anywhere below x equals 0, that is given by region 1. If the particle is found inside our potential well, inside our box, that is given by region 2. And if the particle is found within this section to the right of x equals 0, that is given by region 3. Now, if the particle is in region 1 or in region 3, the potential energy of our particle is equal to a constant given by u naught. But if the particle is inside the potential well, our potential energy of the particle is given by 0. So, in this lecture, our goal will be to basically describe the motion of the particle when it moves along the x-axis, when the particle is found in region 1, 2, or region 3. So, let's begin by discussing region 2. Let's suppose the particle is now inside our finite potential well. So, if the particle is found between the point 0 and now within the following region, the potential energy of that particle is equal to 0. And we know by Schrodinger's equation becomes as follows. So, the first term on the right side basically goes to 0, and we see that our energy of that particle multiplied by the wave function psi is equal to negative h bar squared divided by 2m multiplied by the second derivative of the wave function with respect to x, where m is the mass of that particle, h bar is our constant, and E is the energy of that particle. Now, what exactly is psi? Well, psi is basically the wave function. It's the equation that describes the motion that our particle takes. So basically, if we take this equation and solve this equation in the same way that we solved it for the infinite potential well, we get the following result. So our wave function psi, that is the solution to this Schrodinger equation, is equal to a multiplied by sine of kx plus b multiplied by cosine of kx, where a and b are some unknown constants. So basically, if the particle is found inside the potential well, this is the equation that describes the motion of that particle. Now, let's move on to regions 1 and regions 3. Let's suppose the particle is now found in either one of these 2 regions, and that means that the potential energy u of x is now equal to a constant given by u naught. So if u of x is equal to u naught now, Schrodinger's equation becomes as follows. Now, this quantity no longer disappears. So we have E multiplied by psi equals u naught multiplied by psi minus this entire quantity. So, in the same way that we solve this equation for the solution, we want to take this Schrodinger equation and find what our wave function solution is. So let's basically take these 2 quantities and bring them over to the left side of our equation and set this equal to 0. So we see that h bar squared divided by 2m multiplied by the second derivative of the wave function with respect to x plus E multiplied by psi minus u naught multiplied by psi. Now notice that psi appears on this term as well as on this term, so we can bring that outside of the following 2 quantities. And let's also multiply the left and the right side by negative 2m divided by h bar squared. So if we rearrange this equation and multiply both sides by this, we get the following result. So the second derivative of the wave function with respect to x minus this quantity inside the bracket multiplied by psi, and this is equal to 0. So basically, let's take this entire quantity inside the bracket and set it equal to alpha squared. So we let alpha squared, a constant, equal to 2m divided by h bar squared multiplied by E minus u naught. So basically, if we replace this constant with alpha squared, we get the following Schrodinger equation. And let's call the Schrodinger equation equation 1. So basically, alpha squared is a constant because m is a constant, h bar is a constant, E is a constant, and u naught is also a constant. So if we now take equation 1 and solve equation 1 for the wave function psi, we see that the wave function psi is equal to uppercase C multiplied by E to the power of alpha minus multiplied by x plus uppercase D multiplied by C minus alpha multiplied by x. Now, in the same way that A and B are 2 unknown constants, C and D are also 2 unknown constants, where alpha, that appears on the exponent term, is basically the square root of this entire quantity. So, let's suppose for the time being that the particle is found within region 1. So, if the particle is in region 1, that implies that the x value is always equal to a negative quantity. Now, if the particle begins moving to the left along the x-axis and moves to a quantity of negative infinity, so basically if x approaches negative infinity, we see that this term, E to the power of negative alpha multiplied by x, will basically approach positive infinity. And if this second term is positive infinity, this sign will also be an infinite term. Now, because the wave function cannot actually be infinitely large, because that will be physically not meaningful, we see that this cannot actually be true. And basically, to basically get rid of this negative infinity, we multiply by So this d quantity is equal to 0. So basically, if the particle is found within region 1, this quantity can potentially go to infinity. And to basically get rid of that, this d must be equal to 0. Now, if d is equal to 0, we see that the wave function is simply equal to c multiplied by e to the power of alpha multiplied by x. And this is only true if the particle is found within region 1. Now, by the same exact argument, if the particle is found within region 3, we see that our x value can potentially increase to positive infinity, and now this term has the potential to be equal to positive infinity. And so, to get rid of that, we set c equal to 0. So basically, if the particle is found within region 3, we have to set c equal to 0, and the wave function is equal to d multiplied by e to the power of negative alpha multiplied by x. So, let's stop for a moment and discuss what we were able to obtain so far. So far, we obtained the wave function, the equation that describes the particle's motion when the object is found in region 2. And we also found the wave function for when the particle is found in region 1, and also the wave function that describes when the particle is found in region 3. So basically, we have 3 different wave functions. Now, the entire wave function that is composed of these 3 wave functions we know has to be continuous. So basically, recall that for a wave function to be physically meaningful and measurable, we have to put a certain constraint on that wave function. That is, the wave function must be continuous along the entire x-axis. So that